Hello there. Welcome to Network Security Concepts, Part 2. So perhaps you've heard one of the hundreds of news stories about data security breaches within a large corporation or even a government. Was your credit card number exposed by a breach? How about your private health information? Would you like to know how to prevent these data breaches? The field of network security is growing every day. This module provides a detailed landscape of the types of cybercrime and the many ways we have to fight back against cyber criminals. Let's get started. So welcome to part 2. Okay, so the objectives, so explain how vulnerabilities, threats, and exploits can be mitigated to enhance network security. So on this part 2 of the video lecture, we will be talking about TCP and UDP vulnerabilities, IP services, network security best practices, and cryptography. So let's start with TCP and UDP vulnerabilities. So while some attacks target IP, this topic discusses attacks that target TCP and UDP. TCP segment information appears immediately after the IP header. The fields of the TCP segment and the flags for the control bits fields are displayed on this figure here. So the following are the 6 control bits of the TCP segment. So you've got the URG or urgent pointer field significant, ACK or the acknowledgement, PSH or the push function, RST for the reset, SYN for the synchronized sequence numbers, and FIN, no more data from the sender. TCP provides these services. So you've got reliability delivery, flow control, and stateful communication. So under the reliability delivery, TCP incorporates acknowledgements to guarantee delivery instead of relying on the upper layer protocols to detect and resolve errors. So if a timely acknowledgement is not received, the sender retransmits the data. Requiring acknowledgement of received data can cause substantial delays. Examples of application layer protocols that make use of TCP, or the reliability of TCP includes HTTP, SSL, or TLS, FTP, DNS zone transfers, and others. Flow control. TCP implements flow control to address this issue. Rather than acknowledge one segment at a time, multiple segments can be acknowledged with a single acknowledgement segment. Stateful communication. TCP stateful communication between the two parties occurs during the TCP three-way handshake. So before data can be transferred using TCP, a three-way handshake opens the TCP connection. And then if both sides agree to the TCP connection, data can be sent and received by both parties using TCP. Now, a TCP connection is established in 3 steps as shown in the diagram here. So the first one would be the initiating client requests a client to server communication session with the server. The server then acknowledges the client to server communication session and requests a server to client communication session. The initiating client acknowledges the server to client communication. This is an example of a three-way handshaking. How about TCP Syn Flood Attacks, or the TCP attacks? Network applications use TCP or UDP ports. Threat actors conduct port scans of target devices to discover which services they offer. So the TCP Syn Flood attack exploits the TCP three-way handshake presented in the earlier diagram. Now the figure here shows a threat actor continually sending TCP Syn session request packets with a randomly spoofed source IP address to target. Okay, now the target device replies with TCP Syn acknowledgement packet to the spoofed IP address and waits for the TCP acknowledgement packet. Okay, now those responses never arrive. Eventually, the target host is overwhelmed with half-open TCP connections, and TCP services are denied to legitimate users. Okay? How about terminating a TCP connection? Terminating a TCP session uses the following four-way exchange process. First, when the client has no more data to send in the stream, it sends a segment with the FIN flag set. Okay? Now the server sends an acknowledgement to acknowledge the receipt of the FIN to terminate the session from client to server. The server sends FIN or FIN to the client to terminate the server to client session. And then last would be the client responds with an ACK or acknowledgement to acknowledge the FIN from the server. So the TCP Session Hijacking is another TCP vulnerability. Although difficult to conduct, a threat actor takes over an already authenticated host as it communicates with the target. The threat actor must spoof the IP address of one host, predict the next sequence number, and send an ACK to the other host. If successful, the threat actor could send but not receive data from the target device. UDP segment header and operation. So UDP is commonly used by DNS, TFTP, NFS, right, and SNMP. So it is also used with real-time applications such as media streaming or VoIP. UDP is a connectionless transport layer protocol. It has much lower overhead than TCP because it is not connected or connection-oriented and does not offer the sophisticated retransmission, sequencing, and flow control mechanisms that provides reliability. The UDP segment structure shown in this figure here is much smaller than TCP segment structure. Although UDP is normally called unreliable, in contrast to TCP's reliability, this does not mean that the application that use UDP are always unreliable. Nor does it mean that UDP is an inferior protocol. It means that these functions are not provided by the transport layer protocol and must be implemented elsewhere if required. So the low overhead of UDP makes it very desirable for protocols that make simple requests and reply transactions. So for example, using TCP for DHCP would introduce unnecessary network traffic. So if no response is received, the device resends the request. How about UDP attacks? So UDP is not protected by any encryption. You can add encryption to UDP, but it is not available by default. So the lack of encryption means that anyone can see the traffic, change it, and send it onto each destination. So changing the data in the traffic will alter the 16-bit checksum. But the checksum is optional and is not always used. So when the checksum is used, the threat actor can create a new checksum based on the new data payload and then record it in a header as a new checksum. So the destination device will find that the checksum matches the data without knowing that the data has been altered. So this type of attack is not widely used. Okay? Now for the UDP flood attacks, you are more likely to see a UDP flood attack. In a UDP flood attack, all the resources in the network are consumed. So if the threat actor must use a tool like UDP Unicorn or low orbit ion cannon, these tools send a flood of UDP packets, often from a spoofed host to a server on the subset. The program will sweep through all the known ports trying to find closed ports. This will cause the server to reply with ICMP port unreachable message. Because there are many closed ports on the server, this creates a lot of traffic on the segment, which uses up most of the bandwidth. So the result is similar to the denial of service attack. IP services. One of the IP services is the ARP, or the Address Resolution Protocol, vulnerabilities. So earlier in this module, you learned about vulnerabilities with IP, TCP, and UDP. So the TCP protocol suite was never built for security. Therefore, the services that IP uses for addressing functions such as ARP, DNS, and DHCP are also not secure, as you will learn in this topic. Hosts broadcasts an ARP request to other hosts on the segment to determine the MAC address of the host with a particular IP address. All hosts on the subnet received and processed the ARP requests. The host with the matching IP address in the ARP request sends an ARP reply. Now, here's the ARP process. So any client can send unsolicited ARP reply called gratuitous ARP. This is often done when a device first boot up to inform all other devices on the network or local network of the new device's MAC address. When a host sends a gratuitous ARP, other hosts on the subnet store the MAC address and IP address contained in the gratuitous ARP in their ARP tables. So this feature of ARP also means that any host can claim to be the owner of any IP or MAC address. So a threat actor can poison the ARP cache of the devices on the local network, creating a man-in-the-middle attack to redirect traffic. So the goal is to target a victim, or a host, and have it change its default gateway to the threat actor's device. So this positions the threat actor in between the victim and all other systems outside the local subnet. Next is ARP cache poisoning. ARP cache poisoning can be used to launch various man-in-the-middle attacks. Okay, so in this diagram here, we have the ARP request. The figure shows how ARP cache poisoning works. So PCA requires the MAC address of its default gateway, which is connected to R1. Therefore, it sends an ARP request for the MAC address of 192.168.10.1. And then there would be an ARP reply. In this figure, R1 updates its ARP cache with the IP address and MAC address of PCA. R1 sends an ARP reply to PCA, which then updates its ARP cache with the IP address and MAC address of R1. Alright, so how about if there would be a spoofed gratuitous ARP replies? So in the figure, the threat actor sends two spoofed gratuitous ARP replies using its own MAC address for the indicated destination IP address. So PCA updates its ARP cache with its default gateway, which is now pointing to the threat actor's host MAC address. So R1 also updates its ARP cache with the IP address of PCA, pointing to the threat actor's MAC address. So the threat actor's host is executing an ARP poisoning attack. So the ARP poisoning attack can be passive or active. So passive ARP poisoning is where threat actors steal confidential information. Active ARP poisoning is where threat actors modify the data in transit or inject malicious data. DNS attacks. So the domain name service or DNS protocol defines an automated service that matches resource names such as www.education.com or any URL with the required numeric network address such as IPv4 or IPv6 addresses. It includes the format for queries, responses, and data, and uses resource records or RR to identify the type of the DNS response. Securing a DNS is often overlooked. However, it is crucial to the operation of the network and should be secured accordingly. DNS attacks includes the following. You'll have the DNS Open Resolver attacks, the DNS Stealth Attacks, DNS Domain Shadowing Attacks, and DNS Tunneling Attacks. Now let's talk about the DNS Open Resolver attacks. Many organizations use the services of publicly open DNS servers, such as Google DNS, which is at 8.8.8.8, to provide responses to queries. This type of DNS server is called an open resolver. A DNS open resolver answers queries from clients outside of its administrative domain. DNS open resolvers are vulnerable to multiple malicious activities, as described here on this table. This includes the DNS cache positioning attacks, wherein threat actors send spoofed, falsified record resource or RR to a DNS resolver to redirect users from legitimate sites to malicious sites. So the next one is the DNS amplification and reflection attacks. This is where the threat actors use the denial of service or the distributed denial of service attacks on DNS open resolvers to increase the volume of attacks and to hide the true score or source of an attack. So threat actor sends DNS messages to the open resolvers using the IP address of a target host. So the next one is the DNS resource utilization attacks. So the denial of service attacks that consumes the resources of the DNS open resolvers. This denial of service attack consumes all the available resources to negatively affect the operations of the DNS open resolver. Now, the impact of this denial of service attack may require the DNS open resolver to be rebooted or services to be stopped and restarted. The next type of attack is the DNS Stealth Attacks. So to hide their identity, threat actors also use the DNS stealth techniques described in the table to carry out their attacks. So first would be the fast flags. This is where the threat actors use this technique to hide their phishing and malware. Okay, so that is delivery sites behind a quickly changing network of compromised. Okay, so which is the DNS hosts. Now, the DNS IP addresses are continuously changed within minutes. Botnets often employ a fast flags technique to effectively hide malicious servers from being detected. Next would be a double IP flags. So this is where the threat actors, okay, use techniques to rapidly change the host name to IP address mappings and to also change the authoritative name server. This increases the difficulty to identify the source of the attack. So the last one would be a domain generation algorithms. Threat actors use this technique in malware to randomly generate domain names that can then be used and rendezvous points to their command and control, or the CNC server. Now, the DNS domain shadowing attacks involves a threat actor gathering domain account credentials in order to silently create multiple subdomains to be used during the attacks. So these subdomains typically point to malicious servers without alerting the actual owner of the parent domain. Next would be DNS tunneling. So threat actors who use DNS tunneling place non-DNS traffic within the DNS traffic. So this method often circumvents security solutions when a threat actor wishes to communicate with bots inside a protected network or exfiltrate data from the organization, such as password databases. So when the threat actor uses DNS tunneling, the different types of DNS records are altered. This is how DNS tunneling works for CNC commands sent to a bootnet. Okay? So the command data is split into multiple encoded chunks. Each chunk is placed into a lower level domain name. Okay? Or it is placed on the lower level domain name label of the DNS query. Because there is no response from the local network DNS for the query, the request is sent to the ISP's recursive DNS servers. Now, the recursive DNS service will forward the query to the threat actor's authoritative name server. The process is repeated until all the queries containing the chunks of data are sent. So when the threat actor's authoritative name server receives the DNS queries from the infected devices, it sends responses to each DNS query, which contain the encapsulated, encoded CNC commands. So the malware on the compromised host recombines the chunks, okay, or the chunks of data, and executes the commands hidden within the DNS record. Now, to stop this DNS tunneling, the network administrator must use filter that inspects DNS traffic. So pay close attention to DNS queries that are no longer than the average, or those that have a suspicious domain name. DNS solutions like the Cisco Open DNS black match of the DNS tunneling traffic by identifying suspicious domain. Next IP services is DHCP, or the Dynamic Host Configuration Protocol. DHCP servers dynamically provide IP configuration information to clients. Now, the figure here shows the typical sequence of DHCP message exchange between the client, right, and the server. Now, in the figure, the client broadcasts a DHCP discover message. The DHCP server responds with a unicast, okay, or unicast offer that includes addressing information the client can use. The client broadcasts a DHCP requests to tell the server that the client accepts the offer. Now, lastly, the server will respond with a unicast acknowledgement accepting the requests. Now, what are the attacks on DHCP? So the first one is DHCP spoofing attack. This occurs when a rogue DHCP server is connected to the network and provides false IP configuration parameters to legitimate clients. So a rogue server can provide a variety of misleading information. Next is wrong default gateway. Now, threat actors provide an invalid gateway or IP address of each host to create a man-in-the-middle attack. This may go entirely undetected as the intruder intercepts the data flow through the network. Next would be a wrong DNS server. So threat actor provides an incorrect DNS server addresses pointing the user to a malicious website. Okay. Next would be wrong IP address. Now, threat actor provides an invalid IP address, invalid default gateway IP address, or both. The threat actor then creates a denial of service attack on the DHCP client. Now, assume a threat actor has successfully connected to a rogue DHCP server to a switch port on the same subnet as the target clients. So the goal of the rogue server is to provide clients with false IP configuration information. Now, in the figure here, okay, so the client broadcasts DHCP discovery message. Okay, in the figure, a legitimate client connects to the network and requires IP configuration parameters. Now, the client broadcasts a DHCP discover requests looking for a response from the DHCP server. Both servers receive the message. All right. Second, DHCP server responds with offer. Okay, so let's start with DHCP server here, responding with offers. Now, the figure shows how the legitimate and the rogue DHCP server each respond with valid IP configuration parameters. So the DHCP server here, which is the legitimate DHCP server, will respond, and so with the rogue DHCP server of the threat actor. Now, the client replies to the first offer received, and this client is not aware whether the offer came from a rogue DHCP server. Next would be the client accepts the rogue DHCP requests. Now, in this scenario, the client received the rogue offers first. It broadcasts a DHCP request accepting the parameters, which is from the rogue server. Now, the legitimate and the rogue server each receive the request. And next would be the rogue DHCP acknowledges the request. All right. Network security best practices. Now, on this segment, we will be talking about the network security best practices. So this includes the CIA, or the confidentiality, availability, and integrity. Now, it is true that the list of network attack types is long, but there are many best practices that you can use to defend your network, as you will learn in this topic. Now, network security consists of protecting information and information systems from authorized access, use, disclosure, disruption, modification, or destruction. Most organizations follow the CIA information security triad, or confidentiality, integrity, and availability. Now, let us define confidentiality. So what is confidentiality? So this means only authorized individuals or users, entities, or processes can access sensitive information. It may require using cryptographic encryption algorithms such as AES to encrypt and decrypt data. When you say integrity, this refers to protecting data from unauthorized alteration. It requires the use of cryptographic hashing algorithms such as SHA or SHA. And availability. Authorized users must have uninterrupted access to important resources and data. It requires implementing redundant services, gateways, and links. Okay, So how about the defense in-depth approach? Now, to ensure a secure communication across both private and public networks, you must secure devices including routers, okay, switches, servers, and hosts. This is this is also known as the layered approach. Okay, so it requires a combination of networking devices and services working together. Now consider the network here in the given diagram. So several security devices and services are implemented to protect an organization's users and assets against TCP/IP threats. So it includes VPN. What is a VPN? So VPN is a router used to provide secure VPN services with corporate sites and remote access support for remote users using a secure encrypted tunnels. You can also have the ASA firewall. So this is a dedicated device which provides stateful firewall services. It ensures that internal traffic can go out and come back, but external traffic cannot initiate connections to inside hosts. Next is IPS. An intrusion prevention system, IPS, monitors incoming and outgoing traffic looking for malware, network attack signatures, and more. If it is recognized as a threat, it can immediately stop it. Okay? Next is ENSA or WSA. The email service or email security appliance ENSA filters spam and suspicious emails. The web security appliance or WSA filters known and suspicious internet malware sites. Next is AAA server. So this server contains a secure database of who is authorized to access and manage network devices. Network devices authenticate administrative users using their databases. So all network devices, including the router and switches, are hardened, which means that they have been secured to prevent threat actors from gaining access and tampering with the devices. So next, you must secure the data as it travels across various links. So this may include internal traffic, but is more important to protect the data that travels outside of the organization to branch sites, telecommuter sites, and partner sites. Firewall. So a firewall is a system or group of systems that enforces an access control policy between networks. Okay? Now, all firewalls share some common properties. So firewalls are resistant to network attacks. Firewalls are the only transit points between internal corporate networks and external networks because all traffic flows through the firewall. So firewalls enforce the access control policy. There are several benefits of using firewall in a network. So first, they prevent exposure of sensitive hosts, resources, and application to untrusted users. They sanitize protocol flow, which prevents the exploitation of protocol flaws. They block malicious data from servers and clients. They reduce security management complexity by offloading most of the network access control to a few firewalls in the network. So firewalls also present some limitations. Okay? A misconfigured firewall can have serious consequences for the network, such as becoming a single point of failure. So the data from many applications cannot be passed through the firewall securely. Users might proactively search for ways around the firewall to receive blocked material, which exposes the network to potential attack. Network performance can slow down. Unauthorized traffic can be tunneled or hidden so that it appears as legitimate traffic through the firewall. Next is IPS, or the Intrusion Prevention System. So to prevent data, or to defend, okay, so against the fast-moving and evolving attacks, you may need cost-effective detection and prevention systems such as Intrusion Detection Systems, or IDS, or the most scalable Intrusion Prevention System, or IPS. Now, the network architecture integrates these solutions into the entry and exit points of the network. So the IPS and the IDS technologies share several characteristics. Okay? So IDS and IPS technologies are both deployed as sensors. An IDS or IPS sensor can be in the form of several different devices. It could be in the form of a router configured with Cisco iOS IPS software. A device is specifically designed to provide a dedicated IDS or IPS services. A network module installed in an adaptive security appliance or ASA, switch, or router. Now the figure shows how an IPS handles denied traffic. So the threat actor here sends a packet destined to the target laptop. So here's our target. So the IPS intercepts the traffic, okay, and evaluates it against known threats and the configured policies. So the IPS sends a log message to the management console, and then the IPS drops the packet. Now, IDS and IPS technologies detect patterns in network traffic using signatures. A signature is a set of rules that an IDS or IPS uses to detect malicious activity. Signatures can be used to detect severe breaches of security, to detect common network attacks, and to gather information. So IDS and IPS technologies can detect atomic signature patterns or single packet, or the composite signature patterns. We call it the multi-packet. Content security devices. So content security appliances include fine-grained control over email and web browsing for an organization's users. So this includes the Cisco Email Security Appliance, or ENSA. Now, this email security appliance is a special device designed to monitor Simple Mail Transfer Protocol, or SMTP. So the ESA is constantly updated by real-time feeds from the Cisco Talos, which detects and correlates threats and solutions by using a worldwide database monitoring system. Now, this threat intelligence data is pulled by the Cisco ESA every 3 to 5 minutes. Now, referring to the figure here, okay, so in here, the threat actor sends a phishing attack to an important host on the network. And then the firewall forwards all email to the ESA. Now, the ESA analyzes the email, logs it, and discards it. The next component would be the Cisco Web Security Appliance, or the WSA. Now, the Cisco Web Security Appliance is a mitigation technology for web-based threats. It helps organizations address the challenges of securing and controlling web traffic. Now, this WSA combines advanced malware protection, application visibility and control, acceptable use policy control, and reporting. WSA provides complete control over how users access the internet. Certain features and applications such as chat, messaging, video, and audio can be allowed, restricted with time and bandwidth limits, or blocked according to the organization's requirements. The WSA can perform blacklisting. Okay, that includes the URL filtering, malware scanning, URL categorization, web application filtering, and encryption and decryption of the web traffic. Now, from the figure here, a user attempts to connect to a website. Okay, the firewall forwards the website request to the WSA. Now the WSA evaluates the URL and determines that it is non-blacklisted site. So the WSA disregards or discards the packet and sends an access denied message to the user. On this section, we will be talking about cryptography. Early in the previous topic, cryptography is mentioned as part of the CIA, or the Confidentiality, Integrity, and Availability Information Security Triad. In this topic, we will get deeper dive into many types of cryptography and how they are used to secure the network. Securing communications. Organization must provide supports to secure the data as it travels across the links. So this may include internal traffic, but it is even more important to protect the data that travels outside the organization to branch sites, telecommuter sites, and partner sites. Now, these are the 4 elements of a secure communication. First, there should be data integrity. So data integrity guarantees that the message was not altered. Any changes to data in transit will be detected. Integrity is ensured by implementing either Message Digest version 5 or MD5 or the secure hash algorithm or SHA, hash generating algorithms. Second is origin authentication. It guarantees that the message is not forgery, right, or is not forged and does actually come from whom it states. Many modern networks ensure authentication with protocols such as hash message authentication code or the HMAC. Next would be data confidentiality. So guarantees that the only authorized users can read the message. If the message is intercepted, it cannot be deciphered within a reasonable amount of time. So data confidentiality is implemented using symmetric and asymmetric encryption algorithm. So the last one would be data non-repudiation. It guarantees that the sender cannot repudiate or refute the validity of the message sent. Non-repudiation relies on the fact that only the sender has the unique characteristics or signature for how that message is treated. So cryptography can be used almost anywhere that there is data communication. In fact, the trend is towards all communications being encrypted. Okay, so let's focus on data integrity. Hash functions are used to ensure the integrity of a message. So they guarantee the message data has not changed accidentally or intentionally. Okay, now in the figure here, the sender is sending $100 of money. Okay, and then it transferred to the other or the recipient. Okay, in here, if you will observe, from 100, okay, paid to Alex, okay, and then you've got there paid to Jeremy. It was changed or altered from the $100 to $1,000. Okay, so the sender wants to ensure that the message is not altered on its way to the receiver or recipient. Now, the sending device inputs the message into a hashing algorithm and computes its fixed length hash. Okay, so which is this 4EHI DX67NM-OP9. All right. Now, this hash is then attached to the message and sent it to the receiver. Both the message and the hash are in plain text. Now, the receiving device removes the hash from the message and inputs the message into the same hashing algorithm. If the computed hash is equal, to the one that is attached to the message, then the message has not been altered while in transit. If the hashes are not equal, as shown in the figure, all right, so they are not the same, okay, so then the integrity of the message can no longer be trusted. So it was altered while in transit. Okay, so a hash function. There are three well-known hash functions. You've got the MD5 with 128-bit digest, SHA hashing algorithm, and the SHA-2. Okay, now the MD5 with 128-bit digest is a one-way function that produces a 128-bit hash message. MD5 is a legacy algorithm that should only be used when no better alternatives are available. So use SHA-2 instead. Okay, now SHA hashing algorithm, or SHA-1, is very similar to the MD5 hash functions. So SHA-1 creates a 160-bit hashed message and is slightly slower than MD5. SHA-1 has the known flaws and is a legacy algorithm. That's why we are recommending the use of SHA-2. Okay, now SHA-2 includes SHA-224 or 224-bit, 256-bit, 384-bit, 512-bit. Okay, so SHA-256, 384, and 512 are the next generation algorithm and should be used whenever possible. Now, while hashing can be used to detect accidental changes, it cannot be used to guard against deliberate changes. This means that anyone can compute a hash for any data if they have the correct hash function. Therefore, hashing is vulnerable to man-in-the-middle or MITM attacks and does not provide security to transmitted data. Okay, now I have here an example. So these are the three well-known hash functions. So let's start with the MD5 128-bit digest. So MD5 is a one-way function that produces 128-bit hash message, as shown in the figure. All right. Now MD5 is a legacy algorithm, as mentioned earlier, that should only be used when no better alternatives are available. So we are recommending the use of SHA-2. So in the figure, a plain text message is passed through MD5 hash function. Okay, the result is a 128-bit hashed message. Next is the SHA hashing algorithm. SHA-1 is very similar to MD5. Okay, so several versions exists. You've got SHA-1 creates 160-bit hashed message and is slightly slower than MD5. So SHA-1 has known flaws and is also a legacy algorithm. So again, we are recommending the use of SHA-2. Now in the figure, a plain text message is passed through the SHA hash function. So the result is a hashed message. Third would be SHA-2. This includes SHA-224, as discussed earlier, 256, 384, and 512. So these are the next generation of algorithms and should be used whenever possible. Okay. Now, while hashing can be used to detect accidental changes, it cannot be used to guard against deliberate changes. There is no unique identifying information from the sender in the hashing procedures. This means that anyone can compute a hash for any data if they have the correct hash function. For example, when the message traverses the network, a potential threat actor could intercept the message, right? So change it, recalculate the hash, and append it to the message. The receiving device will only validate against whatever hash is appended. So take note. So therefore, hashing is vulnerable to man-in-the-middle attack and does not provide security to transmitted data. So to provide integrity and origin authentication, something more is required, right? So next would be origin authentication. So to add authentication to the integrity assurance, use a keyed hash message authentication code, or the HMAC. Okay? HMAC uses an additional secret key as input to the hash function. So only parties who have access to the secret key can compute the digest of an HMAC function. This defeats the man-in-the-middle attack and provides authentication of the origin or data origin. Okay? Now, as shown in the figure, the HMAC is calculated using any cryptographic algorithm that combines cryptographic hash function with a secret key. Hash functions are the basis of the protection mechanism for HMAC. Only the sender and the receiver know the secret key, and the output of the hash function now depends on the input data and the secret key. So only parties who have access to the secret key can compute the digest of an HMAC function. Okay, so as mentioned earlier, this will defeat, the man-in-the-middle attacks and provides authentication of the data origin. Okay, so also mentioned earlier, if two parties share a secret key and use the HMAC functions for authentication, a properly constructed HMAC digest of a message that a party has received indicates that the other party was the originator of the message. So this is because the other party possesses the secret key. Now, how do we create the HMAC value? Now, as shown here in the diagram, the sending device inputs data such as Terry Smith, pay, 100, and the secret key. Okay, we've got a secret key there. Now, this has been into the hashing algorithm and calculates the fixed length HMAC digest. So this authenticated digest is then attached to the message and sent to the receiver. Verifying the HMAC value. Now again in the figure, the receiving device removes the digest from the message and uses the plain text message with its secret key as input into the same hashing function. Now, if the digest that is calculated by the receiving device is equal to the digest that was sent, the message has not been altered. Okay? So additionally, the origin of the message is authenticated because only the sender possesses a copy of the shared secret key. Now, the HMAC function has to ensure the authenticity of the message. So next would be the Cisco router HMAC example here. Now the figure shows how HMACs are used by Cisco routers that are configured to use the Open Shortest Path First or OSPF routing protocol routing authentication. Okay. Now in here, R1 is sending a link state updates or LSU regarding a route to network 10.2.0.0/16. Okay, so R1 calculates the hash value using the LSU message and the secret key. Okay, now the resulting hash value is sent with the LSU to router 2. Now router 2 calculates the hash value using the LSU and its secret key. So R2 accepts the update if the hash value matched. If they do not match, then R2 discards the update. Data confidentiality. So there are two classes of encryption used to provide data confidentiality. So these two classes differ in how they use keys. Okay, so you've got symmetric, such as DES, 3DES, and AES or the Advanced Encryption Standard. Okay, so these are based on the premise that each communicating party shows the pre-shared key. So data confidentiality can also be ensured using asymmetric algorithms, including, okay, so the Rivest, Shamir, and Adelman, or the RSA, and the public key infrastructure, or the PKI. Okay, now the figure here highlights some differences between each encryption algorithm method. So one of the most notable difference is, of course, symmetrical uses the same key and asymmetric uses different keys. All right. So symmetric key lengths are short, 40 bits to 256, while for asymmetric, it's 512 to 4096 bits. Okay, so symmetric is faster than asymmetric encryption. Asymmetric, computationally tasking, okay, therefore slower than symmetrical. So symmetric is commonly used for encrypting bulk data, such as in the VPN traffic. And asymmetric is commonly used in a quick data transaction, such as HTTPS when accessing your bank data. Let's dig into symmetric encryption. So symmetric algorithms use the same pre-shared key to encrypt and decrypt data. So a pre-shared key, also called secret key, is known by the sender and the receiver before any encrypted communication can take place. So to help illustrate how symmetric encryption works, consider an example here. Okay, so assuming that we have here Alice and Bob live on different locations and want to exchange secret messages with one another through the email system. Now in this example, Alice wants to send a secret message to Bob. Okay, now in the figure, Alice and Bob have identical keys, okay, to a single padlock. These keys were exchanged prior to sending any secret messages. So Alice writes a secret message and put it in a small box that she locks using the padlock with her key. Okay, now she mails the box to Bob. The message is safely locked inside the box as the box makes its way through the post office system. Now when Bob receives the box, he uses his key to unlock the padlock and retrieve the message. Bob can use the same box and padlock to send secret reply to Alice. Okay? Now, today, symmetric encryption algorithms are commonly used with VPN traffic. This is because symmetric algorithms use less CPU resources than asymmetric encryption algorithms. So encryption and decryption of data is fast when using a VPN. When using symmetric encryption algorithms, like any other type of encryption, the longer the key, the longer it will take for someone to discover the key. So most encryption keys are between 112 and 256 bits. So to ensure that the encryption is safe, use a minimum key length of 128 bits. So use a longer key for more secure communication. Well-known symmetric encryption algorithms are described in the table. So you've got DES, okay, 3DES, AES, SEAL, and you've got the Rivest Cipher or RC. Okay. Now DES is a legacy symmetric encryption algorithm. 3DES is the newer version of DES, but it repeats the DES algorithm process 3 times. Okay. AES, or the Advanced Encryption Standard, is a secure and more efficient algorithm than 3DES. It is popular and recommended symmetric encryption algorithm. So next is SEAL, or the Software Optimized Encryption Algorithm. This is faster alternative symmetric encryption algorithm to 3DES, DES, and AES. The last one would be the Rivest Ciphers, or RC series algorithm. This algorithm was developed by Ron Rivest. So several variations have been developed, but RC4 is the most prevalent in use. So RC4 is a stream, cipher, and is used to secure web traffic in SSL and TLS. Let's get deeper into asymmetric encryption. So asymmetric algorithms, also called public key algorithms, are designed so that the key that is used for encryption is different from the key that is used for decryption. Okay, so as shown on this diagram here. Now the decryption key cannot, in any reasonable amount of time, be calculated from the encryption key and vice versa. So asymmetric algorithms use a public key and a private key. So both keys are capable of encryption process, but the complementary paired key is required for decryption. So the process is also reversible. So data encryption with a public key requires the private key to decrypt. So asymmetric algorithms achieve confidentiality, authentication, and integrity by using this process. Okay, now because neither party has a shared secret, very long key lengths must be used. So asymmetric encryption can use key lengths between 512 to 4096 bits. So key lengths greater than or equal to 1024 bits can be trusted, while shorter key lengths are considered unreliable. Alright, so what are the examples of protocols that use asymmetric key algorithms? So this includes the IKE, or the Internet Key Exchange. This is a fundamental component of IPsec VPNs. So the next one is SSL, or the Secure Socket Layer. So this protocol provides a secure remote access connection to network devices. Okay. Next is SSH, or the Secure Shell. This protocol provides a secure remote access connection to network devices. You also have this Pretty Good Privacy, or PGP. This computer program provides a cryptographic privacy and authentication. It is often used to increase the security of email communications. So asymmetric algorithms are substantially slower than symmetric algorithms. Their design is based on computational problems such as factoring extremely large numbers or computing discrete logarithms of extremely large numbers. So because they are slow, asymmetric algorithms are typically used in low-volume cryptographic mechanisms such as digital signatures and key exchange. Okay. However, the key management for asymmetric algorithms tends to be simpler than symmetric algorithms, because usually one of the two encryption or decryption keys can be made public. So common examples of asymmetric encryption algorithms includes also Diffie-Hellman, or the DH, right? You've got DSS, or the digital signature standard, and digital signature algorithms. You have the RSA, reverse Shamir and Adelman encryption algorithm. You've got the EI-Gamal and the elliptical curve techniques. Okay. Now, the Diffie-Hellman algorithm allows two parties to agree on a key that they can use to encrypt messages they want to send to each other. So the security of this algorithm depends on the assumption that it is easy to raise number of certain power, but difficult to compute which power was used given the number and the outcome. Now, DSS specifies DSA, as the algorithm for digital signatures. So DSA is a public key algorithm based on the EI-Gamal signature scheme. So signature creation speed is similar to RSA, but is 10 to 40 times slower for verification. Okay. Next is RSA. RSA is for public key cryptography that is based on the current difficulty of factoring very large numbers. So it is the first algorithm known to be suitable for signing as well as encryption. Okay, it is widely used in electronic commerce protocols and is believed to be the secure given sufficiently long keys and the use of up-to-date implementations. Right? So next would be the EI-GAMAL. Okay, this is an asymmetric key encryption algorithm for public key cryptography, which is based on the Diffie-Hellman key agreement. So the disadvantage of the EI-GAMAL system is that the encryption message becomes very big, about twice the size of the original message, and for this reason, it is only used for small messages such as secret keys. Alright, so the larger the length, the secure. Okay, the more secure it is. So the last one would be elliptical curve techniques. So elliptic curve cryptography can be used to adopt many cryptographic algorithms, such as Diffie-Hellman or EI-GAMAL. So the main advantage of elliptic curve cryptography is that the keys can be much smaller. Now, Diffie-Hellman is an asymmetric mathematical algorithm where two computers generate an identical shared key without having communicated before. Okay, so the new shared key is never actually exchanged between the sender and the receiver. However, because both parties know it, they can be used by an encryption algorithm to encrypt traffic between the two systems. Right? So here are the three examples of instances when DH is commonly used. First, data is exchanged using IPsec VPN. Okay. Second, data is encrypted on the internet using either SSL or TLS. And third, SSH data is exchanged. Okay. Now the Diffie-Hellman uses unbelievably large number of in its calculations. Unfortunately, asymmetric key systems are extremely slow for any sort of bulk encryption. So therefore, it is common to encrypt the bulk of the traffic using symmetric algorithms such as 3DES, AES, and then use Diffie-Hellman or DH algorithm to create keys that will be used by encryption algorithms. Now, to help illustrate how DH operates, so refer to the figure here. All right. Now, the colors in the figure will be used instead of complex long numbers to simplify the DH key agreement process. Okay. Now, the DH key exchange begins with Alice and Bob agreeing on an arbitrary common color that does not need to be kept secret. Okay. Now, the agreed on color, okay, in our example is yellow, for instance. Right. Next, Alice and Bob will each select a secret color. Okay. So Alice chooses red and Bob chooses blue here. Now, these secret colors will never be shared with anyone. The secret color represents the chosen secret private. Right. So what will happen next is that Alice and Bob now mix the shared common color. Okay. So yellow with the respective secret color to produce a private color. So therefore, Alice will mix the yellow one with her red color to produce a private color of orange. Alright. Now Bob will mix the yellow and the blue to produce a private color green. Now Alice sends her private color orange to Bob and Bob sends her private or his private color green to Alice. Alright. Now Alice and Bob each mix the color they received with their own. So original secret color, red for Alice and blue for Bob. The result is the final brown mixture. Alright, that is identical to the other's final color mixture. So the brown color represents the resulting shared secret key between Bob and Alice. So DH or Diffie-Hellman security uses unbelievably large number in its calculations. For example, a DH 1024-bit number is roughly equal to a decimal number of 309 digits. Alright, so considering that a billion is 10 decimal digits, one can easily imagine the complexity of working with not one but many 309-digit decimal numbers. Now, unfortunately, asymmetric key systems are extremely slow for any sort of bulk encryption. So therefore, it is common to encrypt the bulk of the traffic using the symmetric algorithm. Okay, so as mentioned earlier, 3DES or AES, and then use DH algorithm to create keys that will be used by an encryption algorithm. So that's the end of this video lecture. Thank you for watching and listening. Have a great day.